Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. We discovered a problem with our multi-GPU parallel computing method in our last video, and in this video, we'll address this problem and develop a new approach for multi-GPU parallel computing. It's important to note that only the values of matrix C change during matrix multiplication. Therefore, our focus is primarily on this matrix. The program begins by initializing matrix C to zeros, which is represented by a blue matrix in the figure. In OpenMP parallel computing, matrix C is stored in shared memory, allowing both CPUs on the node to access it. Consequently, all CPU cores, and thus all threads, are able to read from and write to matrix C. We begin by transferring the matrices, including matrix C, to the GPUs using the enter data directive and the map to option, illustrated by the blue arrow. The first GPU is assigned the task of processing the first half of matrix C, while the second GPU handles the second half. During the matrix multiplication, shown by the red arrow, the zeros in matrix C are replaced with new numbers, which are highlighted by the green color in the figure. Each GPU performs computations on its respective half of matrix C. After the matrix multiplication, the resulting green matrix C is transferred back to the CPUs, as shown by the blue arrow. This transfer signifies the execution of multi-GPU parallel computing, where the original blue matrix has been updated to the green matrix. However, there is a significant oversight in this process, as the matrix multiplication was not successful. We assumed that the GPUs on the same node share memory, enabling both GPUs to access matrix C simultaneously. This assumption is incorrect, underscoring a key difference in memory handling between CPUs and GPUs. Let's examine what actually happened during our multi-GPU parallel computing process. Initially, the blue matrix filled with zeros is duplicated and transferred to each GPU. During the matrix multiplication, the first GPU updates the first half of the matrix with new numbers, transforming it into a mix of green and blue. Simultaneously, the second GPU updates the second half with new numbers, resulting in a matrix that is part blue and part green. Consequently, matrix C on the first GPU differs from that on the second GPU. When these two distinct matrices are combined back on the CPUs, the data from the first GPU may overwrite some entries from the second GPU and vice versa. This leads to the final matrix C on the CPUs displaying a mixed pattern of green and blue. We assumed that GPUs on the same node share memory, which, as we've now explained, caused errors in our method. Therefore, we need to refine our approach for multi-GPU parallel computing. To improve our multi-GPU parallel computing method and ensure that the resulting matrix C is uniformly green, we need to introduce a smaller matrix, CR, which is half the size of matrix C. We start by initializing matrix CR with zeros, turning it blue. We then employ the OpenMP framework, using the parallel do directive with the private option to ensure that each thread operates on its own private copy of matrix CR. Black arrows represent this step. Next, each thread transfers its private matrix CR to its designated GPU, as indicated by the blue arrows. During the matrix multiplication, indicated by red arrows, the first GPU updates the matrix CR, which corresponds to the first half of matrix C. Simultaneously, the second GPU updates the matrix CR that corresponds to the second half of matrix C. As a result, the matrix CR on the first GPU is different from that on the second GPU, as each represents a distinct part of the complete matrix C. The matrices CR are transferred back to their respective threads. As indicated by blue arrows, thread 1 receives the matrix CR corresponding to the first half of matrix C, and thread 2 receives the matrix CR corresponding to the second half. Since these threads share memory on the CPUs, it is crucial to ensure that thread 1 assigns the values from its matrix CR to the first half of matrix C. Similarly, thread 2 must assign the values from its matrix CR to the second half of matrix C. This coordinated assignment, as indicated by orange arrows, ensures the successful execution of multi-GPU parallel computing for matrix multiplication. This will be our updated method for multi-GPU parallel computing. In our previous video, we created a new directory named GPU Parallel OpenMP within the work folder on Saga. We will use this directory to submit job scripts and investigate our new approach to multi-GPU parallel computing on the A-100 nodes. This directory now contains two Fortran programs. The first Fortran program with file ending 4 uses our earlier approach to multi-GPU parallel computing, which mistakenly assumed shared memory across GPUs on the same node. To address this misconception, I have created a new Fortran program with file ending 5 that utilizes our updated method. Let's examine our updated method through the new Fortran program designed for multi-GPU parallel computing. First, we need to include the OpenMP library, as we have done before. Then, we'll set the matrix dimension parameter n to 16,384, just like in our previous video. The new Fortran program includes a parameter to set the number of GPUs, similar to our previous program. Given that we are utilizing multi-threading with OpenMP, the number of GPUs is restricted to those available on a single node. On the A100 nodes, we can utilize up to 4 GPUs, as each node is equipped with 4 GPUs. In the program, we have defined some new variables for multi-GPU parallel computing. We will explain the purpose of these variables as we go through the program. We have defined the reduced matrix CR as a dynamically allocatable matrix. This approach allows its dimensions to be adjusted based on the number of GPUs we decide to use. The A100 nodes have 32 CPU cores. We can use 8 CPU cores per GPU while keeping the billing factor at 8. We'll set the number of threads directly in the Fortran program by calling a subroutine from the OpenMP library. The number of threads is set to match the number of CPU cores used in the initialization loop, since this loop will not be offloaded to the GPUs. We'll include the OpenMP directive parallel do in the initialization loop, so it executes in parallel on the CPU cores. The reduced dimension, Rn, will be calculated as the matrix dimension, n, divided by the number of GPUs used by the program. After calculating the reduced dimension, Rn, we can then allocate the reduced matrix CR. We must set all elements of the reduced matrix, CR, to 0 before using this matrix in the multiplication loop. We'll adjust the number of threads to match the number of GPUs by calling the same subroutine from the OpenMP library. The number of threads is corresponding with the number of GPUs, since the matrix multiplication loop will be offloaded to these GPUs. We'll initiate parallel GPU offloading using the parallel directive with the private option. This option guarantees that the variables thread number and offset are unique to each thread. Additionally, it's crucial to ensure that the matrix CR is private for each thread in this program. The thread number is obtained using a function from the OpenMP library and acts as an identifier for each thread. We need to assign each thread to a specific GPU device, ensuring that the computations performed by each thread are offloaded to a GPU. This setup facilitates multi-GPU parallel computing. To link each thread to a GPU, we will utilize a subroutine from the OpenMP library. The offset variable is calculated as the thread number multiplied by the reduced dimension, Rn. We will use both offset and reduced dimension in the matrix multiplication. We'll use the same OpenMP target directives for offloading as in our previous video. Note that in the outermost loop, we are using the variables JR and Rn. The loop order is JR, I, and K, as in our previous video, but now the J loop has become the JR loop. We apply the collapse directive to combine the JR and I loops. Given that multiple threads or GPUs are involved in the matrix multiplication, it's crucial to ensure that the matrix CR represents different sections of the complete matrix C for each thread or GPU. This is achieved by setting J equal to offset plus JR. This ensures that each thread uses different J values, preventing them from performing identical computations. We utilize a double-nested loop to update the values of the complete matrix C based on the values from the reduced matrices, CR, which are specific to each thread. Once again, we use the variables JR and Rn in the outermost loop. Because the threads share memory on the CPUs, it is essential to ensure that each thread assigns the values from its matrix CR to distinct sections of the complete matrix C. This differentiation is achieved by setting J equal to offset plus JR. We conclude the parallel GPU offloading using the N-parallel directive. After that, the program continues as before, with the output of the C matrix. The testing Python script uses the same settings as in our previous video, with the exception that the file ending is now 5. The job script remains the same, utilizing 16 CPU cores and 2 GPUs on the A-100 nodes, but we've increased the memory allocation from 8 GB to 16 GB. We'll discuss this increase and execute the testing process as a batch job in our next video. I am looking forward to the next video, wishing you all happy computing in the meantime.